Every distant galaxy in the sky is rushing away from us, and the farther one sits, the faster it flees. A galaxy twice as far recedes about twice as fast, and this holds in every direction we look, with no galaxy at the center of the flight and none at any edge. The light from the most distant ones arrives stretched and reddened, its waves pulled longer by all the new space that opened up while it crossed to us. That stretching is the expansion of the universe, measured and confirmed for nearly 100 years, and it means that yesterday everything was a little closer together, and the day before that closer still, back to a beginning when all of it was packed to a single searing density. Run the same expansion forward, and the distances only grow, the galaxies scattering ever wider into what looks, to anyone picturing it, like an emptiness waiting to be filled, which raises the question that will not let go once it takes hold. If the whole universe is swelling outward, then surely there is somewhere it is swelling into. So what lies on the outside, and what is all of this space expanding into? Tonight we are going to take that question seriously and follow it all the way down to its root. By the end of this you will understand why the universe is not expanding into anything at all, why there is no edge racing outward and no surrounding emptiness waiting to be filled, and why the beginning we call the Big Bang happened everywhere in space at once rather than at a single point you could ever travel back to. You will also see the honest limits of what we know, the questions about the shape and the size of the universe that remain genuinely open, and why even the word outside may not point at anything real. None of this leans on exotic ideas. It follows from what the expansion actually is, taken at face value and carried through without flinching. If a question that dissolves the more honestly you look at it is the kind you enjoy sitting with, a quiet subscribe helps these find the people who feel the same. Now, let us begin. Point a telescope at a galaxy 100 million light years away and split its light into a spectrum, and the dark lines that mark its elements sit shifted toward the red end, lengthened from where they should be. Point at one twice as far and the shift is about twice as large. The pattern is clean and it holds in every direction. The farther a galaxy lies, the faster it is moving away from us, in a straight proportion that Edwin Hubble and Georges Lemaitre pinned down nearly 100 years ago. A galaxy twice as distant flees twice as fast. One 10 times as distant flees 10 times as fast. This is the basic measured fact of the universe at large, and everything tonight grows out of it. The reddening of that light is the key, and it is worth being exact about what causes it. The waves did not stretch because the galaxy is speeding away through space like a siren passing in the street. They stretched because the space the light was crossing grew while the light was in flight, pulling the waves longer along with it. A photon that left its galaxy when the universe was half its present size arrives with its wavelength doubled, stretched by the same factor the universe stretched during the crossing. The redshift is a record of how much space opened up along the way. It is the expansion written directly into the light. That distinction matters because it changes what is moving. Galaxies are not flying outward through a fixed emptiness from some central blast. The space between them is swelling, carrying them apart the way marks on a stretching sheet draw away from each other, while none of them travels across the sheet. This is why the recession looks the same from every galaxy. An observer in any of those distant galaxies sees exactly what we see, every other galaxy fleeing from them, themselves apparently at the center. There is no special galaxy that everything else runs from. Every point sees itself as the still point and all the rest in retreat, which is the signature of space itself growing rather than objects scattering from a spot. There is a consequence here that sounds impossible until you see why it is allowed. Galaxies far enough away recede faster than light. If every stretch of space between here and there is growing, then add up enough stretches and the total speed of separation passes the speed of light, and beyond a certain distance it does. Nothing is breaking the rule that forbids moving through space faster than light, because none of these galaxies is moving through space at all in the relevant sense. The space itself is expanding, and expansion has no speed limit. The galaxies sit nearly still in their own neighborhoods, while the distance between them runs away faster than any signal could ever close it. The whole of this expansion is captured by a single number that cosmologists track, the scale factor, which is simply how large any given distance is at one time compared to another. When the scale factor doubles, every distance between unbound objects doubles. When it was a tenth of its present value, the universe was 10 times more compact in every direction. Run the scale factor backward, and everything crowds together toward that first dense state. Run it forward, and everything draws apart. One number, rising steadily, stands in for the growth of all space. It is worth being precise about how we know the recession at all, because the whole edifice rests on measuring distances to things tremendously far away. The trick is to find objects whose true brightness we already know, so that how dim they appear tells us how far off they are. Certain pulsing stars beat slower the brighter they truly are, a clock you can read across millions of light years, and a certain kind of exploding star always detonates at nearly the same brightness, a standard flare visible across much of the universe. Measure how faint these appear, work out the distance, then measure the redshift of the galaxy that holds them, and the two together give the recession at that distance. Stack enough of these measurements across enough galaxies and the straight line relation emerges, recession rising with distance. The rate of that rise is a single number, how fast the expansion carries things apart for each step of distance, and it sits near 70 kilometers per second for every megaparsec of separation. A megaparsec is about 3 million light years, so a galaxy that far away recedes at roughly 70 kilometers every second, one twice as far at twice that, and so on up the scale. That number sets the pace of the whole expansion, and through it the age of the universe, since running the growth backward at that rate lands on a beginning about 14 billion years ago. There is an honest wrinkle in that number worth flagging, because it is one of the live arguments in the field right now. Measured one way, by reading the rate directly from nearby galaxies and their standard flares, the expansion comes out a little faster. Measured another way, by reading it off the oldest light and the early universe, it comes out a little slower. The two disagree by more than their stated uncertainties, a gap of several percent that has stubbornly refused to close as the measurements have sharpened. Nobody yet knows whether this points to an error hiding in one of the methods, or to something missing from our account of the universe. It is a real and unresolved tension, and it sits right at the foundation of everything built on the expansion rate. There is a clean way the expansion proves itself beyond the redshift alone, and it comes from watching distant explosions tick. When one of those standard exploding stars detonates, it brightens and fades on a known schedule, a light curve that always runs for about the same number of days. If the expansion is real and stretches the light from distant ones, it should stretch their timing too, slowing the whole event as seen from here. That is exactly what we find. A supernova, whose light is stretched to twice its original wavelength, also takes twice as long to rise and fade as one nearby. The clock of the explosion runs slow, by the same factor its light is reddened, which is what stretching space does, and what a mere local motion would not. This rules out the tired explanations that try to avoid an expanding universe. One old idea held that light simply loses energy and reddens as it crosses great distances, growing weary on the way, which would redden the light without any expansion, but losing energy would not slow the ticking of a distant clock. The stretched light curves of distant supernovae show that time itself, as we observe it out there, is running slow in step with the redshift, which is the fingerprint of expanding space and not of light quietly tiring along its path. So the recession is not a guess read off a single clue. The reddened light, the the slowed explosions, the straight line tying speed to distance, and the agreement of all of it across thousands of galaxies converge on the same conclusion. Space is stretching, and it has been doing so for billions of years, carrying the galaxies apart and lengthening both the light they send and the time we see it unfold in. The expansion is one of the most thoroughly tested facts in all of science, and every independent way of checking it returns the same answer. The rate of the expansion carries a second piece of information beyond how fast galaxies recede. It tells us how long the whole process has been running. Take the present rate of separation and run the growth backward, and you arrive at the moment everything was packed together, about 14 billion years ago. That is where the age of the universe comes from, not from any single clock out there, but from the expansion rate read in reverse. A faster measured rate would imply a younger universe, a slower one an older universe, which is part of why the disagreement over the exact rate matters so much. The number sets the clock on everything. The rate is not actually constant over the life of the universe, despite the name it usually goes by. Early on, with matter dense and its gravity strong, the expansion was decelerating, the growth slowing year by year as everything pulled back on everything else. That deceleration continued for billions of years, the brakes gradually winning. Then, as matter thinned and dark energy came to dominate, the trend reversed, and the expansion began to speed up. So the history of the rate is a long slowing followed by a turn into acceleration, the brakes giving way to the throttle around 6 billion years ago. This means the universe we measure sits at a particular point in a changing story, neither at the fierce deceleration of its youth, nor at the runaway acceleration of its far future, but at the hinge between them. We happen to observe it just after the turn, when dark energy has recently taken the upper hand and the expansion has lately begun to quicken. The rate we measure today is a snapshot of a number that has been falling for most of cosmic history and has only recently started, in a sense, to settle toward the steady pace that an empty, dark energy-dominated universe will eventually hold. The darkness of the night sky is itself evidence about the expanding universe, and the connection is one of the oldest puzzles in the subject. If the universe were infinite, unchanging, and ageless, then every line of sight you followed out into space would eventually land on the surface of a star. With endless stars in every direction, the whole sky should blaze as bright as the sun, with no gaps of dark between the points of light. Yet the night is mostly black, the stars scattered thin across a dark background. That darkness demands an explanation, and a static, endless universe cannot give one. The expanding universe resolves it on two counts. First, the universe has a finite age, so light from the most distant stars has not had time to reach us at all, which means our lines of sight do not run on forever through an endless field of stars, but stop at the edge of what light has had time to cross. Second, the expansion stretches and dims the light from the farthest sources, reddening it and weakening it, so that even the glow that does arrive from great distances is drained of its energy rather than blazing. The sky is dark because the universe began, and because it is stretching the ancient light toward invisibility. So the plain fact that it gets dark at night is quietly tied to the deepest features of the universe, its finite age and its expansion. A truly infinite, unchanging, ageless universe would have a sky on fire from edge to edge. The cool dark we actually see is the signature of a universe that had a beginning and has been growing ever since, dimming and reddening the light of its most distant reaches until the gaps between the nearby stars stay black. The darkness overhead is the expansion written across the whole sky, there to read on any clear night. One honest qualification keeps this from being overstated. The phrase space is stretching is tied to a particular way of carving the universe into moments of time, the natural one for a universe that looks the same everywhere, and it is a description rather than a force pushing on things. and the stretching does not touch what is bound. Atoms hold their size, planets hold their orbits, the Milky Way holds together, and the whole gravitationally bound local group of galaxies stays knit by gravity, untouched by the expansion that carries the distant galaxies away. The growth shows itself only in the great gaps between the bound islands, where nothing holds the distances down. So we have a universe whose every wide gap is opening. The natural next question is the one the cold open asked. If space itself is growing, rather than things moving through it, does that growing space need somewhere to grow into? The word into is doing damage before the question even finishes forming. To expand into something is to grow outward across a space that was already there waiting, the way floodwater runs across a low field that lay there before the water arrived. That image quietly demands an outside, a larger emptiness for the universe to advance through, and the whole difficulty of tonight is that the physics describing the expansion never asks for one. The geometry of an expanding universe is built entirely from the inside, and it needs no surrounding space at all. Here is what built from the inside means in practice. You can measure everything about the shape of a space without ever stepping outside it. Lay out a giant triangle and add up its angles. In flat space, they sum to exactly half a turn. In a positively curved space, they sum to more, and in a negatively curved space to less. Measure how the area of a circle grows as you widen it, or how parallel lines behave over great distances, and you read the curvature of the space directly, all from within. None of these measurements reaches for an outside. The shape of a space is fixed by relationships among points inside it, not by how it sits in some larger arena. General relativity describes the universe in exactly this internal language, and the expansion is simply all those internal distances growing over time. The surface of an inflating balloon is the cleanest way to feel why no outside is required, as long as we use it carefully. Think only of the skin itself, the two-dimensional surface, and put dots on it. As the balloon inflates, every dot moves away from every other dot, and a creature confined to the surface would measure all its neighbours receding, with no dot at the centre of the spreading. That creature could describe the entire expansion of its world, using only distances measured along the surface. It would never need to mention the air inside the balloon, or the around it sits in. The stretching is complete and consistent, told purely from within the skin. Our three-dimensional space works the same way, and this is the leap the mind resists. Just as the balloon skin can stretch without the surface needing a third dimension to stretch into from its own point of view, our three-dimensional space can stretch without needing a fourth dimension of ordinary space to expand through. The expansion is internal in exactly the same sense. Every distance grows, measured by rulers and light inside our space, and the description is whole without any larger volume wrapped around it. There is no wall of our universe pushing outward against anything, because there is nothing the description requires on the far side of any wall. This is where the balloon turns from helpful to misleading, and the honest move is to say so out loud, rather than lean on the image. The balloon, when it comes to mind, hangs in a space, surrounded by air, embedded in our familiar three dimensions. That surrounding space is real for a balloon, and it is exactly the thing reality does not provide for the universe. The balloon is a crutch for the stretching, useful for that and that alone, and the moment you let your eye drift to the air around it, you have imported the very outside the universe lacks. The truer image asks you to keep the receding dots and the growing distances and throw away the surrounding space, the air and the rubber seen from outside. Keep the stretch, drop the surroundings. That is genuinely hard to hold for more than a few seconds, and the difficulty is not a flaw in you. It comes from the mind insisting on a container that the mathematics simply does not contain. The claim that geometry needs no outside has a long pedigree, and it helps to know the idea is not a modern dodge invented to handle cosmology. More than a century and a half ago, mathematicians worked out how to describe curved spaces entirely through measurements taken inside them, with no reference to any larger space holding them. The whole apparatus of curved geometry was built to be intrinsic, defined by how distances and angles behave among the points of the space itself. When general relativity later needed a language for a curving, stretching universe, that intrinsic geometry was waiting, already designed to work without any external arena. You can make the internal test concrete with light, which always takes the straightest available path through space. Send 3 beams to mark out an enormous triangle spanning a good fraction of the visible universe, and measure the 3 angles where they meet. If they add up to a straight half-turn, the space is flat. If they add up to more, the space curves positively, closing toward a sphere. If they add up to less, it curves the other way, flaring open. The beams never leave the space, never consult anything outside it, and yet they report its shape exactly. Curvature is a fact about the inside, readable from within, owing nothing to a beyond. This is the deep reason the demand for an outside misfires. An outside would be needed only if the shape of space could be defined just by how it sits inside a larger space, the way we describe the bend of a sheet of paper by how it curves through the space around it. But space does not work that way. Its shape is fixed by internal relationships, the angles of triangles, the growth of circles, the paths of light, all measured among its own points. The mathematics that describes our expanding universe was deliberately constructed to need nothing on the far side of it, which is why the physics keeps returning the same answer when asked what lies outside. The framework was never built to have an outside in the first place. A useful way to keep the expansion straight in your head is to think of space as a grid that stretches while the galaxies stay put on it. Lay an imaginary grid across the universe, with a galaxy sitting at each crossing of the lines. As the universe expands, the galaxies do not slide across the grid toward the edges. The grid itself stretches, every square growing larger, carrying the crossings apart while each galaxy stays at its own fixed crossing. The galaxies are not traveling anywhere on the grid. The grid is swelling underneath them, and that swelling is the whole of the expansion. This is why it is wrong to think of the galaxies as moving outward through space towards some boundary. On the stretching grid, there is no outward and no boundary to move toward. Every crossing simply gets farther from every other crossing as the squares enlarge, with no crossing nearer to an edge than any other, because the grid has no edge. A galaxy stays at its address on the grid for billions of years while the distance to its neighbours grows, held at its own crossing the whole time, as the space between the addresses keeps stretching it away from them. The grid also makes plain why the question of an outside never arises in the physics. The grid is all there is, the entire arena, and it stretches in place. There is no larger surface it slides across, no surrounding region it expands toward, no outside the grid for it to grow into. It simply becomes more widely spaced everywhere at once. When we ask what the universe expands into, we are treating the grid as if it slid outward across some greater floor, when what actually happens is the grid stretching where it lies, with nothing beneath it and nothing beyond it, only the squares growing and the galaxies riding along at their fixed places. There is a genuine puzzle hidden in the redshift that is worth facing head-on. When light is stretched and reddened by the expansion, it loses energy, and it is fair to ask where that energy goes. A redshifted photon arrives carrying less energy than it set out with, its waves longer, its pitch lowered. Multiply that across all the light in the universe, every beam from every star stretched by the expansion over billions of years, and an enormous amount of energy has apparently gone missing. In everyday physics, energy is never lost, only moved or transformed, so the disappearance looks like a violation of one of the firmest rules we have. The resolution is subtle and a little unsettling. The law that energy is conserved comes from a deep symmetry, the fact that the rules of physics are the same from one moment to the next. An expanding universe quietly breaks that symmetry because it is genuinely different from one era to the next, larger and thinner as time goes on. Where that time symmetry fails, the strict global conservation of energy no longer holds in the way our intuition expects. The energy lost from the stretched light is not hiding somewhere waiting to be found. On the largest scale, in an expanding universe, it is simply not conserved, and that is an accepted consequence of how the expansion works rather than a paradox to be solved. I raise this because it shows how far the expansion reaches into things we treat as bedrock. It is easy to think of expansion as galaxies drifting apart on a fixed stage, leaving everything else just as it is. But the stretching of space touches the light crossing it, draining energy from every photon, and in doing so it bends even the conservation of energy, one of the most trusted principles in science, away from the simple form we learn. The expansion is not a gentle rearrangement of contents, it changes the rules that hold across the whole of space and time. To speak of the distance to a galaxy in an expanding universe, you have to say which distance you mean, because the stretching makes the simple idea split in two. There is the distance the galaxy had when its light set out, and the distance it has now after the expansion carried it farther while the light was in flight. For nearby galaxies, the two are almost the same. For distant ones, they diverge enormously. The galaxy that emitted the oldest light sitting about 46 billion light years away now, while having been far closer when that light departed. Cosmologists handle this with a distance measured on the stretching grid itself, which strips out the expansion and stays fixed for each galaxy even as the actual gap between us grows. There is also the question of when, of what now even means across such reaches, and the expanding universe supplies a natural answer. Because the universe looks the same everywhere on the largest scales, there is a preferred way to slice it into moments, a cosmic time shared by all the observers who see the universe as uniform around them. Each of them can agree on how long it has been since the beginning, 14 billion years, and that shared count gives a common now stretched across the whole of space, a way to speak of the state of the universe at a single cosmic moment, despite the absence of any signal that could synchronize distant clocks directly. This cosmic time is what lets us say the universe is a particular age, or that it was half its present size at a particular moment. Statements that would otherwise have no clear meaning across distances no signal can promptly cross. It is built on the uniformity of the universe, the fact that the same history is unfolding everywhere, so that every observer riding along with the expansion measures the same time since the beginning, the grid that stretches, the galaxies fixed on it, and the shared cosmic clock together give a clean way to describe an expanding universe from the inside without ever needing a vantage outside it. So the geometry needs no outside, builds itself from internal measurements, and describes a universe whose distances all grow, with nothing required beyond them. That removes the container. It raises a sharper question in its place. If there is no surrounding space, and no edge being pushed outward, then where did all this expansion start, and where is the center it has been spreading from ever since? The Big Bang did not happen at a place. This is the single hardest correction to make to the popular account, because the name itself plants a scene of an explosion going off at one spot in a waiting darkness, hurling matter outward into empty space. That scene is wrong in every part. The early universe was not a dense lump sitting somewhere in a void. It was dense everywhere, the whole of space filled uniformly with searing matter, with no center to the heat and no edge to the fire. The expansion was not debris flying away from a point. It was every distance everywhere beginning to grow at once. Hold on to that phrase, everywhere at once, because it dissolves the search for a center. If the whole of space was filled and every part of it began stretching from every other part, then there is no location you could travel to and say the beginning happened here rather than there. It happened at the spot where you are sitting, and equally at every spot a billion light years away, all of it at the same moment. The place where the Big Bang occurred is not somewhere else in the sky, it is everywhere, including right here, because here and everywhere were the same crowded state when it began. The clearest evidence that the beginning had no special spot is written across the entire sky in the oldest light there is. When the universe was about 1/3 of a million years old, it cooled enough for light to travel freely, and that ancient light still arrives today, stretched by all the expansion since into faint microwaves. It comes from every direction at almost exactly the same temperature, a little under 3 degrees above absolute zero, even across regions on opposite sides of the sky. There is no warmer side where the explosion was centered, and no cooler edge where it petered out. The uniformity is the fingerprint of a beginning that filled all of space evenly, with no middle and no rim. That same uniformity is why every observer, everywhere, sees themselves at the center of the expansion. We watch the galaxies flee from us in all directions, and it can feel as though we sit at the heart of it. So does every other observer in every other galaxy, each seeing the same outward rush centered on themselves, each with exactly the same claim to be the middle, which is to say none of them is. A universe with a true center would look different in different directions from most vantages. Ours looks the same in every direction from every point, which is only possible if there is no center at all, the expansion happening evenly through a space with no privileged spot. The same logic strips away the edge. An edge would be a place where the matter stopped and the emptiness began, a boundary you could in principle reach and look past. Nothing in what we see points to one. The universe looks statistically the same in every direction, the same sort of galaxies, the same density, the same ancient glow, with no hint of a boundary anywhere, and no direction in which things thin out toward a rim. A beginning that happened everywhere evenly leaves a universe that is the same everywhere, with no center it expanded from, and no edge it expanded toward. There is a way to locate the Big Bang precisely, and the answer lands strangely. It happened where you are. Trace the history of the patch of space around you backward, and it grows hotter and denser as you rewind, until at the earliest moment it is part of the same searing density that filled everything. Do the same for a patch a billion light years away, and you get the identical story, that distant patch also tracing back to the same hot beginning. Every location runs back to that dense state, because that state was not at one spot. It was the condition of all space at once. So the honest answer to where the Big Bang happened is that it happened here, and equally there, and equally at every point, all of which were the same crowded place when it began. The oldest light makes this visible as a wall that surrounds every observer. When the universe had cooled enough for light to fly free, that release happened everywhere at the same time, so from any vantage, the light from that moment arrives now from a sphere at equal distance in all directions. We sit at the center of our own such sphere, the wall of the early glow ringing us evenly, and an observer in a distant galaxy sits at the center of theirs, shifted to match their position. The wall is not a place in space, it is a time, the moment of release, seen now as a shell around each watcher. That ancient light has been stretched almost beyond recognition on its way here, which fixes how far it has come. It set out as fierce visible and infrared glow from matter at thousands of degrees, and the expansion has lengthened its waves by a factor of more than 1,000, cooling it to the faint microwaves we detect at a little under 3 degrees above absolute zero. That stretch factor is a direct readout of how much the universe has grown since the light was freed, more than 1,000-fold in every direction. The wall of the beginning is not only all around us, it is the most stretched, most travelled light there is, the deepest view backward the universe allows. The evenness of that ancient glow is so extreme that it is itself a puzzle, one that points to something dramatic in the first instant. The light arriving from one side of the sky and the light arriving from the opposite side come from regions that in the standard reckoning were never close enough to have shared heat or settled to a common temperature, since not even light could have crossed between them in the time available, and yet they match to a few parts in 100,000 the same temperature to extraordinary precision, as though they had somehow been in contact. Regions that should never have met agree on their temperature anyway. The leading resolution is that early burst of enormous expansion, inflation, which would have taken a tiny patch already at a single temperature and stretched it in a sliver of a second to encompass everything we now see. On that account, the whole observable universe descends from one small region that had time to even out before the great stretching blew it up to cosmic size. The matching temperatures across the sky are then the echo of that shared origin, a single warm patch inflated until its uniformity spanned the heavens. The very evenness that proves there was no centre also hints at this violent stretching at the start. This matters for tonight because that same early burst is what would have driven the geometry flat. Inflation does two jobs at once. It smooths the universe to the uniformity we measure in the oldest light, and it flattens the curvature towards zero by stretching any initial bend out past detection. The flatness and the evenness, the two facts the rest of this argument leans on, come from the same proposed event in the first fraction of a second. Inflation is not fully proven, and its details remain debated, but it ties together what we see in the ancient light into one account, a brief and ferocious stretching that left the universe smooth, flat, and to all appearances without bound. The part of the universe we can see is almost certainly a small fraction of the whole, and the gap between the two may be enormous. Everything observable, that sphere 46 billion light-years in radius, is only the region whose light has reached us in the time available. The early burst of inflation, if it happened as the evidence suggests, would have stretched the universe so far in its first instant that the whole of it dwarfs the observable patch by an immense factor, possibly hundreds of times larger in every direction, possibly without end. We sit inside a small bubble of visibility within something vastly greater, seeing only as far as light has had time to carry. This reframes the edge of the observable as a horizon of information rather than anything physical. Past it, the same kind of space continues, filled with the same kind of galaxies under the same laws, simply too far for any signal to have crossed to us yet. There is no reason to think our patch is special, no sign that the uniformity we measure to the limit of sight stops just past it. The honest view is of a tiny lit region inside a far larger dark one, the larger part not dark because anything is absent there, but because its light has not had time to arrive. So when we speak of the universe expanding, we are watching the stretching of the small portion we can see and inferring the same for the rest. The whole of it, the part beyond every horizon, expands in the same way, its distance is all growing, whether it is hundreds of times our visible patch or truly infinite. We are in the position of someone reading the weather of an entire ocean from a single patch of water, confident the patterns continue past the horizon while never being able to see them do it. The observable universe is our patch of water. The expansion belongs to the whole ocean, most of which we will never see. There is a sense in which the universe does single out a state of rest, and we can measure our own motion against it, which surprises people who have heard there is no special frame. The oldest light, the microwave glow of the beginning, fills all of space and has a rest frame of its own, the frame in which it looks the same in every direction. We are not quite at rest in that frame. Our galaxy, carried by the gravity of its neighbours, moves through the universe at about 370 kilometers per second relative to that ancient light, and our motion shows up as a slight warming of the glow in the direction we are heading, and a slight cooling in the direction we are leaving. This does not bring back a centre of the universe or an edge, and the distinction is worth holding. The rest frame of the oldest light is not a centre that everything moves around. It is simply the average motion of all the matter in the universe, the frame in which the expansion looks the same in all directions, available at every point in space rather than at one special place. Every observer everywhere can find their own motion relative to it, and there is no location it picks out as the middle. It is a shared standard of rest, not a privileged spot. So the universe offers a way to say how fast you are moving without reference to any landmark, by measuring your drift against the glow of the beginning, while still having no center and no edge. The cosmic rest frame and the absence of a center sit together without conflict. One is about motion, the speed at which you drift through a uniform sea of ancient light. The other is about position, the fact that no point in that sea is more central than any other. The universe lets you measure your speed against the whole while refusing to give the whole a middle. There is a real limit on how much of this we can actually check, and it has to be stated plainly. We can only survey the part of space whose light has had time to reach us, a sphere roughly 46 billion light-years in radius around us. Within that sphere we find no center and no edge, only the same uniform spread in every direction. That there is no edge anywhere, even far past what we can see, is an inference from that uniformity, not something we have directly observed, and it cannot be checked beyond our horizon. Taken as far as the evidence reaches, though, the account is consistent and clear. No center, no edge, the beginning everywhere at once, which forces the next question. If the universe has no edge, is it finite or infinite? And could it somehow be finite and still have no boundary at all? A thing can be finite in size and still have no edge anywhere on it. The surface of a sphere is the plainest example. Its area is finite, a definite number of square units, and yet nowhere on it is there a boundary, a last point where the surface stops. Walk in a straight line across it, and you never reach a wall. You eventually come back to where you started, having circled the whole of it without once finding a rim. Finite and unbounded at the same time, the two words sitting together without contradiction. The surface of a sphere holds that combination, and it is the key to seeing how a whole universe could be finite, yet have no outside. Take that idea up one dimension, which is where it stops being easy to hold and starts being important. A two-dimensional creature living on the surface of a sphere has a finite world with no edge, but the sphere it lives on is curved through a third dimension it cannot point to. Now ask for the three-dimensional version, a space that is finite in total volume, that has no boundary in any direction, and that closes back on itself, so that travelling far enough in a straight line brings you home. This is a closed universe, a three-dimensional space with positive curvature, the direct analogue of the sphere's surface raised by one dimension. It contains a finite amount of space. It has no edge anywhere. A straight path through it returns to its origin. Consider what a beam of light would do in such a universe. Set it loose in one direction and it travels straight forever, never curving, never stopping, never striking any wall, because there is no wall to strike. And if nothing interrupted it and the universe held still, that beam would eventually arrive back at its starting point from the opposite side, having crossed the entire finite extent of space and found no boundary along the way. The path is finite. The wall is nowhere. The light simply goes all the way around. Now bring the expansion back in, because this is the part that answers the question the section was built for. A closed universe can expand without anything outside it to expand into, the same way the surface of a balloon can stretch while staying a closed surface with no edge. As the balloon inflates, its skin grows larger, every point on it spreading from every other, and the surface stays finite and boundless the whole time, never developing a rim. A closed three-dimensional universe does exactly this. Its total volume grows, every distance within it lengthening, while it remains finite and edgeless, and at no moment does it need a surrounding space to grow through. The growth is the swelling of the whole closed shape from within, complete in itself. This dissolves the assumption that finite has to mean walled. A finite universe does not require an edge, does not require an outside, and does not require anywhere to expand into. It can be a closed shape that simply grows, holding a finite volume that gets larger while staying boundless, the way the sphere's surface can be inflated to any size and never gain a border. The container the question keeps demanding is not needed even when the universe is finite. A closed universe would leave a particular fingerprint, and the search for it has come up empty in a way that is itself informative. If space curved back on itself tightly enough, light could travel all the way around and return. So the same galaxy might appear in two different parts of the sky, its light having reached us by two different routes around the closed shape. On the larger scale, the oldest light would carry the same signature, matching circles of pattern in opposite directions, the places where a wrapped universe shows us the same region twice. Surveys of the ancient glow have looked carefully for those matched circles across the whole sky. None has been found. That absence does not rule out a closed universe, but it pins down how large any closed shape would have to be. If space does curve back on itself, the loop is bigger than the part we can see, large enough that light has not had time to travel all the way around even once in the age of the universe. So a closed universe remains allowed, provided it is enormous, far larger than the 46 billion light-year reach of our observation, with its curvature too gentle and its circumference too great to have left any of the telltale repeats we have searched for. This sharpens what the closed model actually offers tonight. It is the clean proof that a finite space can hold no edge and need no outside, the surface of a sphere lifted into 3 dimensions, and it stays geometrically possible for our own universe so long as the shape is enormous. The measurements, though, favour something else. Every test we can run points toward flat rather than curved, and the closed model survives only in the form of a universe so large that its curvature hides below our ability to detect it. The proof of concept stands. The evidence that we live inside it does not. It helps to be clear about what positive curvature would actually do to straight lines, because that is what closing the universe means in practice. On a flat surface, 2 beams of light fired exactly parallel stay parallel forever, never meeting, never separating. On a positively curved surface, like the skin of a sphere, 2 beams that start parallel slowly bend toward each other and eventually cross, the way 2 lines of longitude start parallel at the equator and meet at the pole. A closed 3-dimensional universe does the same thing to light in every direction. Beams that set out parallel gradually converge. Nothing pushes them together. The shape of space itself carries them toward one another. That convergence is the whole reason such a universe is finite, without having a wall, because every straight path eventually curves back. There is no way to travel outward forever, no direction in which you keep going and keep finding new space without limit. The paths all loop. A traveller heading steadily in one direction crosses the entire universe and returns from the other side, having covered a finite total distance and never once met a boundary. The finiteness comes from the curving back, the gentle universal bending of every straight line, rather than from any edge where space stops. So the closed universe answers the old worry that finite must mean walled by replacing the wall with curvature. There is no last point of space, no rim, no barrier. There is only a shape that bends every path home, so that the total amount of space is limited while remaining perfectly boundless. The difference between finite with an edge and finite without one is the difference between a flat sheet that stops at its border and the surface of a ball that simply comes back around. The universe, if it is closed, is the second kind, finite and endless to walk, with its limit hidden in its curvature rather than marked by any edge. The shape of the universe is tied to how much it contains, and this connection is how the geometry was first pursued. There is a particular density of matter and energy, called the critical density, that exactly balances the expansion, and the geometry of space depends on whether the real density falls above, below, or right at it. Above the critical density, the extra gravity bends space into a closed, positively curved shape that is finite and would eventually halt and recollapse. Below it, space opens into a negatively curved shape, infinite and ever expanding. Right at the critical density, space is flat, balanced on the line between the two, expanding forever, but only just. What we measure is that the universe sits astonishingly close to that critical density, which is the same as saying it is flat. Add up everything, the ordinary matter, the dark matter, and the dark energy, and the total comes out within a fraction of a percent of the exact balancing value. The geometry being flat and the density being critical are two ways of stating the one fact, and both say the universe is poised right on the knife edge between the closed shape that would curve back and the open shape that would flare wide. This balance is strange enough to demand explanation, because the flat case is a single exact value between two enormous ranges of alternatives. A universe even slightly off critical density early on would have raced away from flatness as it expanded, curving more and more open or more and more closed as time passed. So finding it still flat after 14 billion years means it began almost perfectly balanced. That extreme fine-tuning is one of the main reasons cosmologists favour the early burst of inflation, which would have driven the density to the critical value naturally, flattening whatever the universe started with. The flatness we measure is more than a fact about shape. It is a clue pointing back to what happened in the first instant. For completeness, it helps to know what the third option would have looked like, the open universe we did not get, because it sharpens what flat and closed each mean. If the universe held less than the critical density, space would curve the opposite way from a sphere into a shape with negative curvature, the three-dimensional version of a saddle that flares outward everywhere at once. On such a surface, two beams of light fired parallel would gradually spread apart rather than staying parallel or converging, and the angles of a great triangle would add up to less than a straight half-turn. An open universe like this would be infinite, expanding forever, its curvature flaring rather than closing. The three possibilities line up neatly against the density. Above critical density, space curves into a closed sphere, finite and bound to recollapse. Below it, space flares into an open saddle, infinite and ever expanding. Exactly at it, space is flat, the knife edge between, infinite in the simplest reading, and expanding forever at an ever-easing pace before dark energy entered the story. Each shape carries a different fate and a different geometry, and which one describes the universe was, for decades, the central question, pursued by weighing how much matter and energy space contained. The answer that came back, flat to a fraction of a percent, places us on the knife edge rather than in either curved case. We are not in the closed universe that would curve back and recollapse, and not in the open saddle that flares wide, but balanced on the flat line between them as far as the most careful measurements can tell. That flat result is what carries the simplest reading toward an infinite universe, and it is what the early burst of inflation predicts. The open and closed universes are the roads not taken, useful for seeing, by contrast, just how finely balanced the flat universe we measure actually is. I have to be careful here, because this is a possibility and not a measured fact, and the honest line between the two matters. Everything just described is what a closed, positively curved universe would be like, and such a universe is allowed by the physics. Whether ours is actually closed is a question for measurement, and our best measurements do not find the gentle curvature that a closed universe would carry. They point somewhere else. So the closed universe earns its place tonight as a proof of concept, the clean demonstration that finiteness needs no edge and expansion needs no outside, even if the real geometry turns out to be different. which means the obvious thing to do next is look at what the measurements actually say. What shape is our universe, as far as we can tell? The same ancient light that proves there is no center also carries the shape of space, and read off it, the answer is flat. Here is how the light measures geometry. The warm and cool patches in that oldest glow have a known true size, set by how far sound could travel through the hot early matter, before the universe cooled and froze the pattern in place. We can calculate that size directly. We also see how large those patches appear in the sky now, after their light has crossed the whole of space to reach us. In flat space, the apparent size matches the true size. In curved space, it would not, because curvature bends the light on its way and swells or shrinks the patches like a lens. The patches arrive looking almost exactly the size they should. The lens, if there is any, is too faint to detect. Put a number on it, and the flatness is severe. The curvature of the universe measures to about 0.0007, give or take 0.0019, which is to say indistinguishable from perfectly flat to within a fraction of a percent. That figure comes from the oldest light combined with the pattern of how galaxies are spread through space, and the two together pin the geometry down tightly. So far as our instruments can tell, the universe is flat, the angles of its great triangles summing to a straight half turn, its parallel lines staying parallel across billions of light years. Flatness is also what the leading account of the early universe predicts, which makes the measurement sit more comfortably than a lone result would. In that account, the universe underwent a brief burst of enormous expansion in its first instant, swelling by a tremendous factor almost instantly. That early stretching would have driven any curvature the universe started with towards zero, flattening it the way blowing up a small balloon to enormous size makes any patch of its surface look flat. A universe that went through that early burst should look flat to us almost regardless of how it began. The geometry we measure and the geometry the early physics predicts agree, two independent reasons pointing at the same flat answer. A flat space, taken at face value, has a plain consequence. It does not close back on itself the way a positively curved universe does, and it does not stop. It has no edge, and it goes on without end. Where the closed universe of the last section was finite and boundless, a flat universe is infinite and boundless, extending forever in every direction, the same kind of space filled with the same kind of matter, past the farthest thing we will ever see and onward without limit. The measurement that says flat says, in its simplest reading, that space is endless. Now the honesty this channel runs on. Flat does not strictly prove infinite, and there are real gaps in the chain. The oldest light taken entirely on its own carries a faint lean toward a closed, finite universe, a hint at the edge of the noise, and that hint only washes out when the galaxy data is folded in. The true geometry could be very slightly curved, closed and finite after all, in a way too gentle for our measurements to have caught yet. A space can be flat in the geometry we measure, and still be finite in its overall shape, folded back on itself through a connection we cannot see from inside, and the overall topology of the universe is genuinely unknown. And underneath all of it sits the hardest limit. We can only measure the patch of space our light has reached, and the geometry past that patch is forever beyond direct test. The flatness measurement comes down to the apparent size of the spots in the oldest light, and it is worth seeing exactly how that size reveals curvature. Those warm and cool patches were set by sound waves in the early matter, and the largest of them have a known true width, calculable from the physics of that early time. They subtend an angle on the sky now of about 1 degree, twice the width of the full moon. That observed angle is the measurement. In flat space, a feature of that true size at that distance would appear at just about that angle. In a positively curved universe, the light paths would bow outward and make the spots look larger than that, and in a negatively curved universe, they would look smaller. The spots come in at the size flat space predicts, which is how we read the geometry as flat. The precision now reachable is what makes the result strong. The spacecraft that mapped the oldest light across the entire sky measured that characteristic angle finely enough to pin the curvature to within a fraction of a percent of perfectly flat. Folding in the separate pattern left by sound waves in the distribution of galaxies, a wholly independent ruler laid across the universe tightens it further. Two different measurements, the angles in the ancient light and the spacing of galaxies, agree that space is flat to the limits of what either can detect. Flat to a fraction of a percent is not flat proven exactly, and the gap between them is where the honesty lives. A curvature too small for these measurements to catch could still be there, leaving the universe very slightly closed and therefore finite, or very slightly open. What the data establish is a tight bound, that any curvature is smaller than a certain small amount, not that it is exactly zero. The simplest reading of a result this close to flat is a universe that is truly flat and therefore endless, and that reading is the standard one, while the measurements themselves can only ever say flat to within their precision, never flat beyond all doubt. Even a perfectly flat universe could be finite, and this is the possibility that keeps the infinite reading honest rather than certain. Flatness is about curvature, the local bending of space, and a space can be flat everywhere in its curvature and still be finite in its overall shape if it wraps around on itself. A flat sheet rolled into a cylinder is still flat in the geometry measured on its surface, with triangles and parallel lines behaving exactly as they do on an open sheet, yet it has become finite in one direction, looping back. A three-dimensional space can do the same, flat in every local measurement, and yet closed up into a finite total volume through a wrapping we have no way to feel from inside. If our flat universe wraps like that, the consequence would be visible in principle, the same way a small closed universe would betray itself. Light could cross the wrapped space and return, so we might see the same galaxy or the same pattern in the oldest light, repeated in different directions, the telltale sign of a space that loops. Searches for those repeats, matched circles in the ancient glow, and duplicated structures in the sky have turned up nothing. So if space is flat and finite, wrapped into some looped shape, the loop is larger than the part we can see, too big to have sent any light all the way around in the age of the universe. This is the topology question, and it is genuinely open. Flat tells us the curvature, the local geometry, and it says nothing on its own about the global shape, whether space runs on without end or quietly closes back on itself somewhere past our horizon. The simplest assumption, and the standard one, is that a flat universe is the ordinary endless kind, infinite in every direction, but a flat, finite, wrapped universe remains allowed by everything we have measured, its loop simply too large for us to have caught. Whether space is truly infinite, or merely larger than we can see, is a question the flatness alone cannot settle. Flatness is a knife edge in time as well as in space, and this is what makes the measured flatness so telling. If the universe had ever departed even slightly from perfectly flat, that departure would have grown. A touch of positive curvature would have deepened toward a closed universe that recollapses. A touch of negative curvature would have flared toward a wide open one. Flatness is unstable, the balance point that any small push drives you away from, so a universe found flat to a fraction of a percent today must have been flat to an extreme precision near the beginning, balanced on the edge to a degree that cries out for a reason. The early burst of inflation supplies that reason cleanly. A brief spell of enormous expansion drives any curvature towards zero with overwhelming force. The way stretching any curved surface to enormous size flattens whatever patch remains in view. Whatever shape the universe held before inflation, the great stretching would have ironed it flat to far beyond the precision we can measure, leaving it balanced on the critical density, not by luck, but by the action of that early expansion. So the flatness that looks like impossible fine-tuning becomes the natural outcome of a process, which is much of why inflation is taken seriously, despite the gaps in its details. This closes a loop worth noticing. The flatness that points to an infinite universe in the simplest reading is also the flatness that points back to inflation in the first instant. And inflation is also what smooths the oldest light to its measured evenness. One proposed event in the first fraction of a second accounts for the flatness, the uniformity, and the apparent endlessness altogether. None of it is fully proven, and the honest caveats stand, but the account hangs together. Several independent features of the universe tracing back to a single violent stretching at the start, after which space was left flat, even, and to all appearances without bound. Dark energy has quietly broken an old link that ran through this whole subject, the tie between the shape of the universe and its fate. For most of the last century, geometry was destiny. A closed universe, dense and positively curved, would expand, slow, halt, and recollapse. An open or flat universe would expand forever, slowing but never stopping. Knowing the shape told you the ending, and the two questions, what shape and what fate, were one question. Measure the curvature and you would know how the universe ends. Dark energy severs that connection. Now a flat universe, instead of coasting to an ever slower expansion, accelerates, pushed apart faster and faster by the energy of space itself. The fate no longer follows from the shape alone, because a new ingredient, the dark energy, has entered and taken control of the long-term future, regardless of the geometry. A flat universe could in principle expand forever at an easing pace, or accelerate toward the cold isolation we now expect, or even recollapse depending on how dark energy behaves and the curvature no longer settles the matter. So the universe being flat tells us its shape, and the simplest reading of its extent, that it is endless, but it no longer tells us how things end. That is now governed by dark energy, the least understood thing in the inventory, which currently points toward the accelerating, emptying future. The clean old correspondence, shape determines fate, has given way to an account where an unknown energy of space writes the ending, and the geometry we have measured so carefully sets the stage without deciding the final act. We know the shape with precision, and the fate only as far as we understand a thing we barely understand at all. So the most we can honestly say is this: the universe is flat as far as we can measure it. Flatness is what the early physics predicts, and the simplest reading of a flat universe is one that is infinite and without end. That reading is standard, it is well supported, and it is still a reading rather than a proven fact. Grant it, as most cosmologists do, and a strange question lands immediately, one that turns the whole topic on its head. If the universe is already infinite, already endless in every direction, then what could it possibly mean for it to be expanding? An infinite universe does not get bigger when it expands. This is the turn the whole video has been climbing toward, and it sounds at first like a contradiction, so let me set it down slowly and plainly. If space is truly infinite now, then it was always infinite, endless yesterday, endless a billion years ago, endless at the very beginning, when it was also unimaginably denser. Infinity is not a size the universe is growing toward. It was already the extent of things at every moment in the past. And something already infinite has no space to become larger, because there is no larger than endless to reach. So what is actually changing when an infinite universe expands? The answer is the spacing, not the size. The scale factor grows, which means every distance between unbound things increases. Galaxies that were closer drawing farther apart, the same matter spreading thinner through the same endless space. Nothing is added at any edge, because there is no edge to add anything at. No new territory opens at a rim, since there is no rim to open at. The universe is not getting larger in extent, It is getting more dilute, the same infinite space holding its galaxies at ever greater separations, thinning out everywhere at once while staying exactly as endless as it always was. This is where the word expanding nearly betrays us, because in ordinary speech, expanding means growing larger, and growing larger means adding volume at an outer edge, the way a balloon adds volume as it inflates. For an infinite universe, none of that applies. There is no outer edge to push, no volume being annexed from outside, no surrounding space being filled. The only honest meaning of expansion here is internal, distances stretching, density falling, the scale factor climbing. Size was never the quantity that changed, because the size was always infinite. What changes is how far apart everything sits within an extent that has no end and never did. Sit with where that leaves the question the whole video has been chasing. We started by asking what the universe is expanding into, expecting some emptiness beyond the edge that the growing universe pushes against, and here the floor gives out from under the question. An infinite universe has no edge to push, occupies no surrounding space, and adds nothing at any boundary because there is no boundary and no outside and no into. The expansion is entirely a matter of internal stretching, the dilution of an endless space with nowhere it advances toward and nothing it advances against. There is no into. The question was looking for a destination the expansion never had. That is the most vertiginous point of all of this, and it is worth feeling fully rather than rushing past. For 5 sections, the mind keeps reaching outward, hunting for the outside, the edge, the somewhere the universe is growing into, and the answer that keeps coming back is that there is no outward to reach. The growth is a swelling from within an endlessness that has no margin, no rim, no beyond, and it advances across nothing because there is nothing for it to advance across. The universe is not expanding into the void. There is no void for it to expand into. There is only more space, opening up between everything, forever, inside a space that was already without end. The single number that tracks the expansion, the scale factor, has a history worth following because it makes the dilution concrete. When the scale factor was half its present value, roughly 6 billion years ago, every distance between unbound galaxies was half what it is now, and the universe was 8 times denser. The same matter packed into a volume 8 times smaller. Wind further back to 1/100th of the present scale, and the universe was 1,000,000 times denser, fierce and hot. The scale factor has been climbing the whole time, and as it climbs, the density of matter falls in step, thinning as the cube of the growth, since every doubling of distance spreads the same matter through 8 times the volume. This is what lets an infinite universe be denser in the past, without ever having been smaller in extent. Infinity does not shrink when you rewind the scale factor. A space that is endless now was endless then, only with its galaxies crowded far closer together, the same boundless extent filled to a far higher density. Run it back toward the beginning, and the density climbs without limit, while the extent stays infinite throughout. An endless space growing hotter and tighter packed, never smaller in total size because there is no total size to shrink. The beginning was not a small universe. It was an infinite one at crushing density. So the growth and the dilution are the same process seen from 2 sides. The scale factor rises, distances lengthen, and the fixed amount of matter in any region spreads thinner, the universe cooling and emptying as it expands. Nothing about this requires or produces a change in the overall extent, which was infinite before and stays infinite after. What changes is only how densely the endless space is filled, falling steadily from the searing crowd of the beginning toward the thin, cold scatter of the far future, the same matter, the same boundless space, ever further apart. An infinite universe holds infinitely many galaxies, and seeing what the expansion does to that count sharpens what growth really means here. If space goes on without end, then it is filled without end, an unbounded number of galaxies scattered through a boundless extent. The expansion does not add to that number. It does not manufacture new galaxies at some frontier or annex fresh territory full of them. The same unbounded collection of galaxies simply drifts farther apart, each one receding from its neighbours as the distances grow, the total tally fixed at infinite while the spacing between them widens. So the expansion changes the spacing of an unchanging census rather than enlarging a growing one. The count stays exactly as it is, endless, while every gap in it stretches. No galaxy is created by the expansion, and none is destroyed, the population holding steady at infinite throughout, only spread thinner and thinner across the same endless space. This is another angle on why bigger is the wrong word. A finite thing gets bigger by adding to itself at the edges. An infinite universe has no edges to add at, and gains nothing it did not already have. It only rearranges what is already endlessly there into an ever sparser pattern. The one direction in which the universe genuinely gains something is time. It does not grow outward into new space, but it does grow older, and the growing is into the future, the one direction with real space ahead. Each moment the distances are a little greater than the moment before, the density a little lower, the galaxies a little farther flung. If the universe is expanding into anything at all, the only honest candidate is the future, the next moment, and the next, the expansion unfolding through time rather than reaching across space. There is no spatial outside for it to enter. There is only the steady forward of time, into which the whole endless arrangement keeps thinning. It is worth standing in a distant galaxy for a moment to see that the expansion plays no favourites, because that symmetry is part of what makes its space itself doing the stretching. From our position, every distant galaxy flees from us, and we sit apparently still at the centre. From the position of any one of those galaxies, the view is identical. They sit still while everything, including our own galaxy, flees from them. Neither of us is right that we are the still centre, and neither is wrong, because there is no still centre to claim. Each observer is at rest where they are, watching the same universal recession open up around them. This even-handedness is the signature that distinguishes stretching space from ordinary motion. If galaxies were truly flying outward through a fixed space from some explosion, there would be a real centre they all fled, and observers at different places would see different things, some near the centre, some out toward the edge of the debris. Nothing like that appears. Every observer everywhere sees themselves at rest, with the same recession in all directions, which is only possible if no one is moving through space at all, and the space between everyone is simply growing. The democracy of the view is the proof that nothing is travelling, and everything is being carried. So there is no galaxy that is the true origin of the expansion, and no galaxy out at some rim, just as there is no centre and no edge to space itself. Every galaxy is an equally valid still point, every observer equally entitled to feel themselves the one fixed thing, while the rest streams away. The expansion treats all positions alike because it is not happening to the galaxies at all. It is happening to the space between them, evenly, everywhere, with no preferred place for it to start from, and no special place for it to reach. The uniformity of the experience across every vantage is the expansion announcing what it actually is. The oldest dream tied to this question is to fly to the edge of the universe and look over it, and it is worth following that flight to see exactly where it fails. Set out in a fast ship in any direction, and keep going. You never reach a wall. You pass through region after region of galaxies, each one looking much like our own neighbourhood. The same kind of stars, the same kind of space. On and on, you cross the place that was once the edge of what we could see from home, and there is nothing there, no boundary, just more universe stretching ahead exactly as before. The edge keeps receding because there is no edge, only the horizon of what light has had time to show, moving with you as you go. What you would find, instead of a boundary, is that every place you reach considers itself the middle. Arrive at the most distant galaxy your old telescopes could detect, and from there the universe spreads in all directions just as it does from home, with that galaxy's own horizon drawn around it, and our galaxy now sitting at the far edge of what it can see. There is no point in the whole of space where the character of things changes, no region that announces itself as the rim, no last galaxy with emptiness beyond. Travel forever, and you find forever more of the same, an endless space with no place in it that is the end. This is the concrete meaning of a universe with no edge, felt as a flight that never arrives at one. The flight to the edge fails because the destination does not exist, not for any want of speed or distance. There is nowhere that is the outside, no boundary to stand at, no over the edge to look past. The expansion is not opening a frontier somewhere ahead that a fast enough ship could catch. It is stretching the whole endless space at once, everywhere, with no leading edge to chase, and no rim to find at the end of any crossing, however long. A question often lurks under all of this, sharper than it first sounds. As the universe expands, is new space actually being created? When two galaxies grow farther apart and more distance opens between them, it can seem as though fresh space must be appearing in the gap, manufactured out of nothing to fill the widening separation. The honest answer is that this is more a matter of how we describe things than a fact about a substance being produced. Space is not a material that gets made by the cubic mile. It is the set of relationships between things, the distances and geometry, and what the expansion does is increase those distances. Whether you say new space is being created or simply that existing distances are growing is largely a choice of words, and the physics is the same under either phrasing. The measured fact is plain. The separation between unbound galaxies increases over time. The scale factor climbs, every gap widens. Calling that the creation of new space is a vivid way to speak, useful sometimes, but it tempts the mind toward treating space as a stuff with an amount which then demands a place for the new stuff to come from, and a place for it to go. There is no such stuff and no such accounting. There are only distances, and they are getting larger. This matters for the central question because the idea of an outside often sneaks in through the idea of created space. If space were a substance being generated, you might ask where it comes from and where the universe puts it, smuggling back the outside through the back entrance. But space is not generated and stored. It is the web of distances among things, and that web is simply stretching, its threads lengthening everywhere at once. No material is being made, no reservoir is being drawn from, and no outside is needed to supply or receive anything, because nothing is being supplied or received. There are only the growing distances of an endless web with no border. Holding this clearly is genuinely difficult, and the difficulty is built into us rather than into the physics. Every growing thing we have ever watched grows by pushing its edge outward into space that was already there. So the mind keeps rebuilding that edge and that clearing even after the argument has removed them. The trick is to keep only the stretching and refuse the edge, to let expansion mean nothing more than distances lengthening everywhere inside a boundless space. Get there, even for a moment, and the original question quietly dissolves rather than gets answered, which is a stranger and more honest resolution than any outside could have been. And it opens a new question with real teeth, the one I want to turn to next. If there is no edge and no into, where do all these fleeing galaxies actually end up, and does the expansion ever stop? There is a question I have been holding back, and it is the one that decides how this story ends. If the universe is not expanding into anything, then where do all these fleeing galaxies actually go? And does the expansion ever ease off? Or does it run away from us for good? Stay with me, because the answer is coming, and it is stranger and lonelier than a simple slowing down. There is a real edge in the sky, and it is the edge of what we can see, not the edge of the universe. Light travels at a fixed speed, and the universe has existed for a finite time, so there is a farthest distance from which light has had the chance to reach us at all. Past that distance, the light simply has not arrived yet, held back only because there has not been enough time since the beginning for it to cross the gap, with nothing ending out there at all. That boundary is called the particle horizon, and it is the true edge of the observable universe, the limit of everything we can in principle detect. It is easy to mistake this horizon for the edge of everything, and the mistake matters, so it is worth separating the two cleanly. The horizon is a limit on seeing, set by the speed of light and the age of the universe. It is not a wall in space, not a place where matter stops, not a boundary the universe runs up against. Beyond it lies more of the same endless universe we have been describing, the same galaxies, the same kind of space, simply too far away for their light to have reached us in the time available. The universe does not end at our horizon, our information about it does. Put the scale to it. The observable universe reaches roughly 46 billion light-years in every direction, making a sphere about 93 billion light-years across. That number surprises people, because the universe is only around 14 billion years old, and light from the edge has been travelling only that long. The resolution is the expansion itself. While that light was in transit, the space it had already crossed kept stretching, carrying its source far further away than the distance the light actually covered. So the matter that emitted the oldest light we catch now sits about 46 billion light-years off. Even though the light itself travelled for under 14 billion years, the horizon is larger than the age alone would suggest, because space grew underneath the travelling light. Every observer everywhere sits at the centre of their own observable sphere. Ours is centred on us, set by our position and the time light has had to reach this spot. A galaxy a few billion light-years away has its own sphere centred on itself, overlapping ours in part, and reaching past it on the far side, taking in regions we will never see while missing regions we can. There is no single shared edge that everyone agrees on, only countless overlapping spheres, each observer marooned at the centre of their own, each taking in a different slice of the one boundless universe. The horizon is personal, a property of where you stand, not a feature of space itself. And the honest limit here is absolute. We cannot see beyond our horizon, not now, not with any instrument, not ever, because the light from out there has not arrived and the expansion is widening the gap. What lies past it is inference, the assumption that the uniform universe we see all the way to the edge keeps going in the same way beyond it. That assumption is reasonable, since everything up to the horizon looks the same in every direction, but it is an assumption that no observation can ever confirm. We are reasoning past the last thing we can check, and we have to be clear that is what we are doing. The reason the observable universe reaches farther than its age in years comes down to a distinction worth drawing carefully between how far light has travelled and how far its source has been carried. The oldest light we catch has been on its way for about 14 billion years, but the galaxy that emitted it has not sat still during that time. The expansion has carried it steadily away, so that by now it lies roughly 46 billion light-years off, far beyond the distance the light itself crossed. The horizon is set by where those sources are now, after all that carrying, which is why it stands at 46 billion light-years even though no light has travelled more than 14 billion. There is a related surprise hiding in which galaxies we can see at all. Many of the galaxies whose light reaches us today are, at this moment, receding from us faster than light, carried by enough intervening space that the gap grows quicker than any signal could close it. We see them only because their light set out long ago, when they were closer and the space between had not yet stretched so far, and that ancient light slipped across to us before the growing distance could outrun it. The light in our telescopes left its sources when the reaching was still possible. The sources themselves now are already beyond the speed of light in their recession. This is why the edge of the visible is a subtle thing rather than a simple sphere of a fixed size. It is built from the whole history of light and expansion together, the speed of light setting how far signals can travel, the growth of space carrying sources outward while the light is in flight, the two effects combining to place the horizon where it sits. The boundary is real and it is sharp, the farthest any light could have reached us from, and it is woven out of motion and stretching across the entire age of the universe, rather than marked by anything standing out there at the edge. There are really 3 different edges in play, and keeping them apart resolves most of the confusion about what we can see, reach, and touch. The first is the edge of what we can see, the particle horizon at about 46 billion light years, the limit of everything whose light has reached us. The second is the edge of what we could ever reach, smaller, set by the accelerating expansion. Even a signal sent now at the speed of light can only ever arrive at galaxies within about 16 billion light years, because everything beyond that is receding faster than the signal can follow. The third is the edge of what we will ever see in the future, larger than today's visible limit, since light still in transit will keep arriving for ages to come. These 3 do not coincide, and the gaps between them carry real meaning. We can see far more of the universe than we could ever travel to, because much of what we observe is already receding beyond any chance of our reaching it, visible only as old light from when it was closer. The galaxies between the 16 billion light-year reach and the 46 billion light-year sightline are there in our sky, their ancient light still arriving, while they themselves are forever beyond contact, places we can watch but never touch and never signal. The future visibility edge stretches farthest of all, to around 60 billion light-years, the limit of everything whose light will ever manage to reach us across all the time to come. Past even that, there are regions whose light will never arrive, sources receding so fast that their signals lose the race for good. So the universe divides into shells around us. What we can reach, a small inner sphere; what we can see now, a larger one; what we will ever see, larger still; and beyond them all, the greater part of an endless universe whose light will never cross to us at all. None of these shells is an edge of space. Every one is an edge of contact, drawn by light and expansion around our particular point. The cosmic event horizon behaves in some ways like the surface of a black hole, turned inside out, and the resemblance is more than poetic. A black hole has a boundary past which nothing can escape outward to reach us. The accelerating universe has a boundary past which nothing can travel inward to reach us. The same kind of one-way surface drawn the other way round. In both cases there is a sphere beyond which events are sealed off from us for good, light unable to cross the divide, and in both cases that surface marks a permanent limit on what can ever be known from where we stand. The likeness runs deep enough that the cosmic horizon, like a black hole's, is thought to carry a faint temperature and a kind of radiation, an extraordinarily cold glow associated with the boundary itself. It is far too faint ever to detect, trillions of times colder than the empty space around us. But the physics that predict a temperature for a black hole's horizon predicts one for the cosmic horizon too. The boundary of what we can reach is not a clean line ruled across nothing. It is a surface with physical properties, a horizon in the full sense, sharing the strange thermodynamics that black holes first revealed. In the far future, as dark energy comes to dominate completely, the universe settles toward a state defined entirely by this horizon, each observer enclosed in a sphere of reachable space, with the cold boundary drawn permanently around them. Everything beyond is gone, sealed off, radiating its faint, impossible chill. The end state of an accelerating universe is in a sense a single black hole horizon seen from the inside, a bounded patch of space, surrounded by a surface nothing crosses, holding whatever did not recede past it, and cut off from everything that did. The expansion that needs no outside ends by wrapping every observer in a horizon of their own. The accelerating expansion has already placed most of the universe permanently out of our reach, and the number of places we could ever travel to is not only finite, but shrinking. Of all the galaxies we can currently see, only those within about 16 billion light years could ever be reached by a ship leaving now at any speed below that of light, because everything farther is receding faster than such a ship could follow. That 16 billion light-year sphere holds a finite haul of galaxies, a large number but a bounded one, and it is the entirety of what our descendants, however advanced, could ever physically visit. Worse, that reachable sphere is contracting in what it contains. As the expansion accelerates, galaxies that sit just inside the reachable boundary today are being carried across it, passing from reachable to forever beyond reach, one by one, with no way back. Every year, a few more galaxies cross that line and are lost to any possible future expedition. The set of places we could in principle go is not holding steady, and certainly not growing. It is quietly diminishing, the universe closing its doors a galaxy at a time, sealing more and more of itself away from any traveller who starts from here. So the practical universe, the part that could ever be touched rather than merely seen, is a finite and dwindling island inside the larger visible one, which is itself a small patch of the endless whole. We can see far more than we can reach, and we can reach less with every passing age. The endless universe that has no edge and no outside is also, from the standpoint of anyone living in it, a universe that is mostly already gone, carried beyond contact by the same expansion that fills it. The reachable part is bounded, the seeable part larger but still bounded, and the whole of it endless, with the gaps between those three only widening as time runs on. There is a strange inversion at the heart of the horizon, worth stating on its own. Nothing can move through space faster than light, the firmest speed limit in physics, and yet the expansion routinely carries distant galaxies away from us, faster than light, because the growth of space obeys no such limit. The one thing that can outrun light is space itself stretching. A galaxy sitting still in its own neighborhood, breaking no rule, can recede from us faster than any signal could chase it, simply because enough space lies between us and it, all of that space swelling at once. The limit binds motion through space and says nothing about the stretching of space. This is why the horizon is permanent rather than a barrier we might one day cross with a faster ship. The fastest thing there is, light, already loses the race against expanding space beyond a certain distance, its beams swimming forward while the space they cross grows faster than they advance. No ship, no signal, nothing held to the speed of light can do what light cannot. The expansion has set a limit that the universe's own speed limit cannot beat, sealing off everything past the horizon with the one process that outpaces light, the quiet, universal stretching of space between every distant thing and every other. So the universe has no edge, while your view of it does, and confusing the two is what makes the edge of the sky feel like the edge of reality. There is one more twist, and it changes the whole future of this account. That horizon is not fixed. The expansion is reshaping it, and the way it is doing so is the strangest and loneliest part of the entire story. What is the expansion doing to the edge of the visible over time? The expansion is speeding up. For most of the 20th century, the open question was how fast it was slowing, since the gravity of all the matter in the universe should be pulling everything back and putting the brakes on the growth. Then in 1998, measurements of distant exploding stars delivered the opposite answer. Those stars, a particular kind of supernova that always burns at a known brightness, appeared fainter than they should if the expansion was slowing, which meant they were farther away than expected, which meant the expansion had been picking up speed rather than easing off. The growth of the universe is accelerating, driven by a dark energy woven through space itself, a property of empty space that pushes the expansion faster as time goes on. An accelerating expansion changes the future completely, and the first thing it changes is what can ever reach us. There is a distance called the cosmic event horizon, beyond which space is receding so fast that light leaving a galaxy there can never reach us, no matter how long it travels, because the space in between grows faster than the light can cross it. Right now, that horizon sits around 16 billion light years away. Any galaxy already beyond it is permanently out of contact, its present light forever unable to arrive. And because the expansion accelerates, that horizon is closing in over time in the sense that matters, with more and more galaxies crossing it and falling silent for good as the growth carries them past the line. Follow this forward, and the sky empties. Galaxy by galaxy, everything not bound to us by gravity is being carried beyond the event horizon, its light stretching toward the red and dimming as it goes, until it fades past any possible detection. The galaxies in our own bound group will eventually merge, the Milky Way and Andromeda drawing together into a single combined galaxy. Everything outside that bound group recedes away and winks out. Roughly 100 billion years from now, an observer in that merged galaxy would look out and find nothing beyond it, the rest of the universe carried so far past the horizon that not a single other galaxy remains visible anywhere in the sky. The cruelty in that future is what it does to knowledge. An observer then, looking out at an empty black sky around a single galaxy, would have no evidence that a wider universe ever existed. The distant galaxies would be gone from view, the oldest light stretched away to nothing, the expansion itself no longer readable because there would be nothing left out there to watch recede. The clues we use today to piece all this together, the fleeing galaxies, the ancient glow, the redshift, would all have slipped beyond reach. The universe will go on being endless and full past that observer's horizon, and they would have no way to know it. The truth becomes permanently undiscoverable, sealed away by the same expansion that produced it. One honest qualification holds this in proportion. This lonely future rests on dark energy behaving as a steady, unchanging property of space, a true constant, which is what current measurements suggest but have not nailed down. If dark energy weakens over time, or strengthens, or shifts in some way we have not yet measured, the far future could look different. The acceleration easing or sharpening, and the timeline bending with it. The behavior of dark energy over the long run is one of the genuine open questions in the science, and the bleakest version of the future is the one where it stays exactly as it appears now. The dark energy driving the acceleration is the largest single component of the universe, and naming its share puts the rest of the contents in proportion. About 68% of the energy of the universe is this dark energy, woven evenly through all of space. Roughly another 27% is dark matter, the unseen mass that holds galaxies together, and only about 5% is the ordinary matter that makes up stars, planets, and everything we have ever touched. So the stuff of the familiar world is a thin minority of the whole, and the dominant ingredient is the very thing pushing the expansion to accelerate, a property of empty space that grows more important as the universe thins out. What makes dark energy accelerate the expansion is that it does not dilute as the universe grows. Ordinary matter spreads thinner as space stretches, its density falling, its pull weakening. Dark energy, so far as we can measure, keeps the same density no matter how much the universe expands, because it appears to be a property of space itself, so every new stretch of space brings its own share of it. As matter thins and its breaking pull fades, this steady energy of space comes to dominate, and its effect is to push distances apart ever faster. Early on, when matter was dense, the expansion slowed. About 6 billion years ago, as matter thinned past a threshold, dark energy took over and the expansion began to speed up. The honest state of knowledge here is that we can measure dark energy's effects precisely while understanding its nature barely at all. We know how much there is and how it behaves, that it stays nearly constant and pushes the expansion faster. We do not know what it is, why it has the value it has, or whether that value is truly fixed for all time. Recent measurements have even hinted that it might be changing slightly over cosmic history, a result not yet settled but taken seriously enough to unsettle the assumption that it is a perfect constant. The acceleration is certain. Its cause remains one of the deepest open problems in all of physics. The far future the acceleration is carrying us toward is not only empty of other galaxies but cold and dark within whatever remains. Stars are finite engines. They burn through their fuel and die, the largest in millions of years, the smallest red dwarfs lasting trillions, and once the gas to make new ones runs thin, no replacements come. The merged remnant of our own group of galaxies will go on forming stars for a long while yet, then slowly redden and dim as its stars age and gutter out, until it becomes a graveyard of cooling embers, white dwarfs fading to black, neutron stars chilling in the dark, the occasional dim flare the only light left. Around that dimming island, the rest of the universe will have vanished from view entirely, carried beyond the horizon by the acceleration, so the long future holds a single aging galaxy alone in a black sky, its own stars dying one by one, with no other galaxy visible anywhere and no fresh light arriving from outside. The universe will still be there, endless and full past the horizon, but every sign of it will have been cut off, the evidence of expansion erased along with the galaxies that displayed it. The universe ends not in fire or collapse, but in isolation and slow cooling, each surviving island sealed in its own widening dark. This is the honest endpoint of an accelerating expansion held constant, and I do not think there is a way to make it warm. The expansion that needs no outside also takes everything outside away, one galaxy at a time, until each remaining patch is left alone with its dying stars and a horizon drawn tight around it. There is no wall it runs into and no void it fills. There is only the steady thinning and cooling of an endless space, the lights going out across it, and the long dark afterwards stretching on with no edge to reach and no outside to escape into. The lonely cold future assumes dark energy holds steady, and if instead it strengthens over time, the ending turns violent in a different way. Should dark energy grow more powerful as the universe ages, a possibility some have taken seriously, the acceleration would intensify without limit, and the horizon would close in tighter and tighter until it began tearing structures apart from the largest scales down. First, the distant galaxies would be ripped beyond reach, then the bound clusters, then individual galaxies torn open, then solar systems pulled apart, then planets and stars, and finally, in the last instant, atoms themselves shredded as the expansion overwhelmed even the forces holding matter together. This scenario carries the name, the Big Rip. In that ending, the expansion stops being a gentle thinning and becomes an active destroyer, the growing space prying apart everything that gravity and the other forces had held. It would arrive at a definite time, a final moment when every bound thing, down to the last atom, is dismantled by space expanding too fast for any force to resist, where the steady dark energy gives a slow cold isolation over endless ages. A strengthening dark energy gives a sharp and total tearing at a fixed date in the finite future. Both are bleak. They are bleak in different ways, one a long fading, the other a violent end. Current measurements favour the steady version, dark energy as a near-perfect constant, which points to the slow cold future rather than the rip. But the behaviour of dark energy over the long run is not nailed down, and recent results have hinted, without yet proving, that it might not be perfectly constant after all. So the exact shape of the end is genuinely uncertain, hanging on the nature of the least understood ingredient in the universe. What is not uncertain is that the expansion in any of its plausible futures carries the universe toward an ending defined by separation, whether the slow kind that isolates or the fast kind that tears apart. The lonely future is real, but it is also unimaginably far off, and setting the timescales against our own makes both facts land. The universe is about 14 billion years old now. The emptying of the sky, the point when other galaxies have vanished beyond the horizon and a lone merged galaxy sits in the dark, lies roughly 100 billion years ahead, more than 7 times the entire age of the universe so far. We are not near that ending. We are in the bright early morning of the universe, when galaxies still crowd the sky and their light still arrives in floods, a privileged and passing chance to see the wider universe at all. Stretch the timescales further and the human measures fall away entirely. The smallest, longest-lived stars, the red dwarfs, will go on burning for trillions of years, far longer than the universe has yet existed, so the era of starlight has barely begun. After the stars finally die, the universe faces ages of darkness so long that the time elapsed so far becomes a rounding error against them. Stretches of cold and quiet, measured in numbers with no feel for the mind to grip. The 14 billion years behind us, the whole history from the beginning to now, is the briefest opening sliver of what lies ahead. So the isolation the expansion is carrying us toward is certain and remote at once, written into the physics and set unthinkably far in the future. That distance in time is not a reprieve that changes the ending, only a measure of how slowly it arrives. The galaxies are crossing the horizon now, the expansion is accelerating now, and the long emptying has already begun, even though its completion lies 100 billion years off. We happen to live early enough to still see the evidence in the narrow dawn before the wider universe slips away, which is part of why the question of what it all is feels so pressing to ask, while the asking is still possible. This answers the question, the hook left open. The expansion does not ease off, and it does not halt. It runs away, faster and faster, carrying the galaxies past the edge of contact and emptying the observable sky over the long ages. A universe that needs no outside to expand also, in the end, erases the very evidence of its own expansion. So we are left with a universe that is endless, edgeless, growing into nothing, and slowly hiding itself from anyone left to look. What does all of that leave us thinking the universe actually is? The word outside may not point at anything. We have spent the whole video hunting for the outside of the universe, the surrounding space it expands into, and coming up empty at every turn. The reason that search keeps failing may be simpler and stranger than any answer it could have found. The universe is the whole of space and time, the totality of everything there is. To ask what lies outside it is to ask for a location where there is no location to be had, a place beyond the set of all places. The question has the grammar of a sensible question and may point at nothing whatsoever. There is a clean way to feel why a properly formed question can still have no answer. Ask what lies north of the North Pole. The words fit together correctly, the sentence breaks no rule of grammar, and yet it picks out nothing, because north is a direction defined on the surface of the Earth, and it simply runs out at the pole. There is no place that is north of the northernmost place. Outside the universe may be exactly this kind of question. Outside is a relation between things within space, and when you apply it to the whole of space at once, it runs out the way north runs out at the pole, with no referent left for it to catch. The same dissolving may apply to the question of what came before the beginning. We treat the Big Bang as an event in time, with an empty stretch before it, the way any event has a yesterday. But if time itself began with the universe, then there is no before to occupy, no earlier moment sitting empty and waiting. Asking what came before is then like asking what lies north of the North Pole in time rather than space, a question whose words work and whose reference never existed. The beginning may not be an event within time, but the edge of time itself, with no prior moment for the question to land on. What all of this exposes is a habit of the human mind rather than a fact about the universe. We are built by a life lived among objects inside space, every one of which has an outside, a surrounding, a before. We take that lifelong pattern and extend it to the universe as a whole, and the pattern simply does not reach that far. The pull we feel toward an outside, the conviction that there must be a somewhere beyond the last galaxy, is the mind running a rule past the only region where the rule applies. The physics offers no outside because the concept, stretched to the whole of everything, finds nothing to hold on to. The question is built from a habit, and the habit does not fit the thing it is being asked about. The idea that time itself began with the universe is the part that makes before the beginning so slippery, and it is worth taking seriously rather than waving away. In general relativity, space and time are stitched together into one fabric, and that fabric is part of the universe, not a stage the universe sits on. Wind the expansion back toward the beginning, and it is not only the matter that crowds together, the fabric of space and time is doing it too, and at the earliest moment our equations describe, that fabric reaches a state where the notion of an earlier time may simply stop applying. If time is part of the universe and the universe has a first moment, then there is no time before it for anything to happen in, no empty stretch waiting because the stretch itself is what begins. This is genuinely hard to hold, and I do not want to oversell how settled it is. Our description of that first moment runs into its own limits, because the physics we have breaks down at the extreme density of the very beginning, where gravity and the quantum world collide, and we have no tested theory to cover both at once. So the honest position is that time beginning with the universe is what our best current framework suggests, while the framework itself goes dark, exactly at the moment we most want to question. We are reasoning right up to the edge of where the known physics holds, and the question of before lands in the region past that edge. There are serious ideas that reach into that region, and none of them is established. Some propose that our universe is one episode in an endless sequence, others that it buds off from an eternally expanding larger structure, others that the beginning is a smooth boundary with no sharp first instant at all. Each is a real attempt by serious people, and each lies, for now, beyond any observation that could confirm or rule it out. So the most truthful thing to say about before the beginning is that our best physics hints there may be no before, that the alternatives remain unproven speculation, and that we are pressed here against a limit we do not yet know how to cross. It is worth separating two very different reasons a question can fail to have an answer, because the outside of the universe may fail in the deeper of the two ways. Some questions have answers we simply cannot reach, like the colour of a flower that bloomed and died on a world whose light will never get to us. The fact is out there, settled, merely hidden. Other questions have no answer because the words do not pick out anything coherent, like asking how much the number 7 weighs. The question of what lies outside the universe may belong to the second kind, where the trouble is not that the answer is hidden, but that the words, applied to the whole of space and time, stop referring to anything at all. The difference matters because it changes what kind of humility is called for. If the outside were merely hidden, we could honestly say there is an answer we will never know. But if outside the totality of space is a phrase that points at nothing, the way north of the North Pole points at nothing, then there is no hidden fact either, no concealed truth we are failing to see. There is just a question built from a habit of language, dressed in correct grammar, reaching for a reference that was never there to find. Saying so is not dodging the question, it is recognizing what kind of question it is. I want to be careful not to claim more than I can defend, because the line between a meaningless question and a merely unanswerable one is itself disputed. Perhaps there is some larger structure, and outside our universe does point at something real, just something we can never observe. Perhaps the totality of space and time genuinely has no outside, and the phrase is empty. We are at the edge of what physics and even language can handle cleanly, and the most honest position holds both possibilities open, while noting that the everyday image, a simple void past the edge that the galaxies fly into, is the one thing the physics fairly clearly rules out. The most serious version of an actual outside comes from the same inflation that may have flattened our universe, and it is worth describing plainly so its limits are clear. In some accounts, the early burst of expansion does not happen only once. It goes on eternally in a larger structure, stopping here and there to form regions like our own, while continuing elsewhere, budding off universe after universe without end, each one a pocket where inflation halted and ordinary space settled out. Our universe, in this account, is one such pocket among endlessly many, and there is, in a sense, something outside it, the wider inflating structure and the other pockets within it. Even granting all of that, it is not the outside the original question reaches for. The question reaches for a simple emptiness past the edge of our space, a void the galaxies are flying into. The inflating structure is nothing like that. It is not a calm emptiness our universe sits in. It is a furiously expanding region in which our entire universe is a single bubble, sealed off from the others by stretches of inflating space growing far faster than light, so that no signal, no traveller, no influence could ever pass between our pocket and any other. If there is an outside in this sense, it is more thoroughly cut off from us than the far side of our own horizon, and it is not a place our expansion advances into. And all of it remains unproven, which has to be said clearly. This never-ending inflation and its endless bubbles is a serious idea held by serious people, built out by extending physics we have some evidence for, and it sits entirely beyond observation. We cannot see another pocket, cannot detect the inflating structure, cannot test whether any of it is real, so the honest final word on an outside is layered. The everyday void past the edge is ruled out. An enormous inflating structure with other universes in it is possible but unproven and unreachable, and in no version is there a surrounding space that our universe is expanding into, because even the wildest real proposal does not give the question the kind of outside it was asking for. Stand back from the whole argument and notice what has happened to the original question along the way. We began wanting to know what lies past the edge of the expanding universe, expecting some emptiness the galaxies rush into. Section by section, the supports under that question have been removed. There is no edge because the beginning happened everywhere, and the universe is the same in all directions with no rim. There is no center the expansion flows out from. There is no surrounding space the geometry requires, no outside the measurements find, and on the simplest reading, no end to space at all. The question kept asking for a somewhere beyond, and at every turn the universe declined to provide one. What is left is not an answer to the question, but a clear view of why it has none. The expansion is the stretching of an endless space from within, every distance growing, the whole thinning and cooling and carrying its galaxies past one another, and eventually past the horizon, with nothing it advances into, because there is no into for it to have. The strangeness the question reached for, out past the last galaxy, turns out to live in the question itself, in the quiet mismatch between a mind built to expect an outside and a universe that simply does not have one. The hunt for the edge ends not at a boundary, but at the recognition that the hunt was looking for the wrong kind of thing. That recognition is where the whole argument has been heading, and it is a stranger destination than any outside could have been. The universe is not an object in a larger space, growing into the emptiness around it. It is the space, all of it, stretching itself apart from within, endless and edgeless and slowly emptying, with no beyond for the mind to escape to. After all the measuring and reasoning, what remains is that single hard fact and the quiet it leaves behind. So let me end where the whole thing started, with that reddened light still arriving, and say what I have come to think it means. Honesty requires marking the edge of even this. This brushes against the limits of language and concept as much as against physics, and there are real open questions underneath it. We do not know whether some larger structure exists beyond our universe, an inflating expanse forever budding off new regions, or other possibilities that serious people take seriously. If something like that is real, it is not the everyday surrounding emptiness the original question has in mind, the simple void past the edge that the galaxies are flying into. It would be something far stranger, and crucially, something we have no way to observe, sealed off from us as completely as anything can be. So the most honest answer refuses the flat claim that nothing lies outside, and says instead that the question, as usually meant, asks for something the universe gives no sign of containing, and may not even be the kind of thing that can contain at all. I find this one strange because the answer is not a fact you can file away beside the others. It is the quiet dissolving of the question itself. We ask what the universe is expanding into because everything we have ever watched grow has grown into something around it. Water spreading across a floor, a crowd spilling into a square, a fire eating outward through dry grass. We carry that picture up to the largest scale there is, and it simply stops working, because there is no floor beneath the universe, and no clearing around it, no waiting space for it to reach into. The expansion happens within, every distance stretching at once, the whole of space growing thinner and more dilute while advancing into nothing at all, since there is no edge to do the advancing, and no outside for it to find. What stays with me is how natural the wrong picture feels, and how hard the true one is to hold for longer than a moment. The mind keeps rebuilding the emptiness past the last galaxy, keeps wanting us somewhere beyond the edge, and the physics keeps gently taking it away. So far as we can tell, the universe is not sitting inside anything. It is the whole of space, all of it, with no banks and no far shore, stretching itself apart in a silence that runs in every direction and stops nowhere. And one distant day, that same reddened light we started with will finish its long fade, and the sky will close quietly around whoever is still there to look. If you would like more of these, a subscribe is the simplest way to keep them coming.